First of all, I would like to thank the organizer for the kind invitations. Thanks to well. I will give a kind of review on dark energy singularities and some of the work I have done recently with my collaborator and the teaching students I also. Well, here is an outline of my talk, so I will start introducing briefly what we know about the universe, and then I will classify the singularities. So the first two talks, Diego and I will be essentially speaking about these dark energy singularities. There are two main types of classification. One that I will follow here, which is essentially based in how some geometrical quantities behave when we approach this. Okay, then I will describe how maybe it's possible to avoid these singularities with some dark energy, dark matter interaction. I will present an example. And whenever we are dealing with singularities, the question we trace is what happens from the quantum side. So if we involve when we approach the tree, then what would happen? I will, on the second point, I will also describe the cosmological perturbation on this side of the point. So what do we know about the universe? So essentially it's homogeneous isotropic on large scales, and these days essentially the universe is essentially isotropic if we assume the cosmological principle. So at large scale it's homogeneous and isotropic. Then what it's made of, so essentially 4% is standard matter that we are made of, and the rest is dark. So we have dark matter that we have heard a lot about it these days, and then something that makes the universe to accelerate. And the simplest option would be to consider dark energy. We can as well invoke modified theory of gravity. But here for most of the talk, my talk it would be on general. How to infer the acceleration of the universe from observation, from the measurement of the Hubble rate, supernova, bars, and so forth. Okay. Now, what happened is that this, within our ignorance, we can describe the dark energy through an effective equation of state, and that equation of state, if we assume W equal dark masses, and the last measurement of Planck essentially stated that W could be roughly is essentially -1. Now, if it's slightly smaller than -1, then some weird behavior could happen in the future if the type of equation of state kept the same behavior for a very long time, keep its behavior in the future. Okay, so in particular, so if we have W as Planck is predicted for the W equal dark matter, so W to the order -1.13. Of course, with the arrow, the cosmological constant is there, therefore W minus 1 is included. But if we stick to values that are slightly smaller than -1, then what happens is that, first of all, the new energy condition is not fulfilled, which means that for homogeneous and isotropic universe, the energy density of this fluid grows as the universe expands. And depending how fast it grows, then the universe might face in the future. Okay. And there are different kind of doomsdays or singularities, and I will essentially focus on the reddish one, okay? The big rip, the little rip, that will define in a moment the little sibling of the big. And the reason I will focus on these three is because they happen if and only if we have photon matter. The other, they can take place in a model in which the null energy condition is fulfilled. Okay? So that was that. And the classification is essentially based on, as I said, the behavior of geometrical quantities. So the Hubble rate is essentially the speed at which we are expanding, or its derivative, so essentially the acceleration at which the expansion is taking place. And this essentially is describing how the curvature behaves. Okay? There are other ways of classifying the singularities by looking at the geodesic, so essentially by looking at the connection. I will rather use this definition. And as I said, I will stick to the reddish one because they happen if and only if we have phantom matter. So they are really intrinsic to that type of matter. So the big group, which is the most famous singularity in this kind of model, so essentially at some point in the future, and at some point which is finite from now, so what's happening is that these quantities, the minus h, the Hubble rate, this derivative blows up. Okay. It's a finite quantity. And this is true singularity. Space-time singularity. Then we have something that I will essentially refer to as an abrupt effect, because it's not strictly space-time singularity, and it's essentially a big group which is sensed to an infinite cosmic time. Okay. So in that case, so essentially we have the divergence of the same quantities, but now at an infinite cosmic time. And the name was given on this paper by Phantom et al. Back in 2011, even though these kind of events were known since the 60s, and it was found by this Russian in a modified theory of gravity, okay? And it was literally on the past. Okay? It can also happen for perfect fluid, where the equation of state deviates from the cosmological constant by a term which is proportional to the square root of the energy density, as Sergei and collaborator showed, and also Stefan showed. And also we showed some years ago that this can happen in Reynolds model. So essentially, if you heard about Reynolds this morning, so if you have a 5-dimensional Reynolds model with a scalar field or a dilaton on the bulk, okay, and you have what is known as an induced gravity term, so depending on the embedding, so what will happen essentially on the past, you have a de Sitter solution, and on the future, the solution will become either asymptotically Minkowski, or it will hit little. Then finally, the last one is the list of siblings of the big group. Again, I will call it this an abrupt event. It's not strictly a singularity, space-time singularity, because it happened at an infinite cosmic time, and it's the smallest one. So essentially what happened in this case is that an infinite size, even though the Hubble parameter blows up, its derivatives are finite. Okay. And here essentially well, there is a table which summarizes the different behavior, and I will stick to the green. So the big group, little signal on the and here essentially I show the behavior of the scale factor in terms of time for these different models. This model dependent, so for the model that we analyze the cosmological perturbation on them, so these were the value. Now if you change the model, okay, so this value will change. Okay, so what do we have? Why we have in common these three, the singularity, big group, and these other two events. So essentially what happens if you have a bonded body, okay? So the motion of these two bonded bodies can be described by an effective potential. That effective potential has a mean. So you have essentially a stellar orbit, and one thing will be turning around the other. Now, due to the expansion, which can be very large, okay, of the universe could at some point superinflate. So essentially what's happening is that this potential at the end will open. Okay? And therefore, the structure will be somehow destroyed. So this was, and this happened on the three models. So no matter if you have space-time singularity or not, so if you have bonded structure, at some point in the future, it will be destroyed. Okay, so this is something intrinsic to this type of model. So what we did recently is to pick up three models that were known and analyze the cosmological perturbation of this one. And to our surprise, so we posted the paper on the 1st of November, and it appears the 3rd of November. 2 days later, we were contacted by new scientists, because they got some interest on the work. So essentially, after all, it seems like people care about what could happen in the future. Okay? And this had a domino effect to our surprise. So 2 days later, we appeared on the news of several places all around the world. Okay? And this came to a surprise to Emmanuel Alvaran, João Moraes, and myself, the two students that I'm currently surprised. And as I'm Spanish, so I thought, okay, in a statistic way, so I made the un abanico, I don't know what's the word in English. Fun? Okay. Well, so what we did, so essentially, we pick up three models, okay? The simplest one that we can think of. The big group, so essentially, W combined matter with W constant and smaller than -1, and with the value of Planck, so that's 1.013, should be not 1 Then the little rip, and the simplest option would be this kind of equation of state, so a deviation from cosmological constant, where the deviation is described by the square root of the energy density, black energy. And then finally the little zero of the validity, which is essentially a deviation from the cosmological constant by constant, okay, which is negative. So these are the three models that we consider, and we worked out the perturbation. So I will avoid the calculation. I will try as much as possible to stick just to figure, except on the last part that will be about continuous knowledge. So we did first order perturbation. So we choose the Newtonian gauge, and we have three types of matter. So we have dark energy, dark matter, and we include radiation because we started our numerical integration since the radiation dominated epoch till now. Why? Because we wanted to obtain the matter power spectrum. That is okay. Then we have to be careful because we are dealing with dark energy, even described through fluid, and the speed of sound can be negative, describe the speed of sound. So to be able to make the calculation, what we did is what is usually done in W called dark matter with W larger than -1, which is we assume that behind this model there is a kind of scalar field, and even if you have a phantom scalar field, its speed of sound will be squared will be 1, and we plug that number and we carry on the calculation. So that's essentially what we did. Okay. And the results, maybe it's not from the back, you cannot see them. So essentially, as I said, we have three components: dark matter, dark energy, and radiation. And to each one will have its associated velocity. We solved the equation since back in the radiation dominated epoch till now. In fact, we now would be here. The zero would be essentially here, here, and here. So even we carry our numerical solution a bit into the future to see what would happen with the solution. So on this part here corresponds to the big rip model. This one, the little rip, and this one, the little signal of the big rip. This corresponds to the evolution of the density contract for dark matter, here the corresponding one for dark energy, and finally how the gravitational potential behaves. Okay? For different scales, ranging roughly from 0.1 megaparsec -1 to 10 to -4. So the sooner a given scale exits the horizon, so the faster, the more it will grow, okay? Which is small. So when it crosses the horizon, it will grow fast. So this is common to essentially the three model, and the later they enter, so the less they will cross. And this is the part corresponding, as I said, to dark energy and the gravitational potentials. And these normalize to its value back in the past. So essentially we have a plateau, the radiation dominates area, that plateau will decrease, dark energy, and then it will decrease again. We are on an expanding universe, so as one would expect, the gravitational potential now is much weaker. So the next thing we did was to compare with the matter power spectrum that we will get from an Landesidian. And well, the deviation were quite small. So the one that approached better the Landesidian, or deviate less from the Landesidian, as you can imagine, the later signal of the big one. Why? Because it has the smoother behavior, and its equation of state is closer to -1. And so forth. As we deviate from Landesidian, we have a larger deviation. So the reddish one corresponds to the little rip, and then the blue one corresponds to the little signal of the big. Okay? So this. We also obtain F sigma 8. So essentially, when you look at the matter power spectrum, you have, for the different scale, you are looking at their behavior at present. While with F sigma 8, you pick up a scale, and then you look for its evolution. Okay. And for the three model, we got more or less the fit properly. So this one was fitting better, but the reason essentially that when we looked at the value considered in this model and this one, for the value that we used for the fit using Planck, while this one it was fitted a few years before and it was using the W map. Okay? We are currently doing the fitting with the same data to compare. My guess, but it's just a guess, I might be wrong, is that this one, the little signal of the big one, will be the one that fit better. So this is essentially what happened from the perturbation point of view for the simplest model. Now, a question that would rise is what happened to this model if, or can we somehow remove this model? So there are two ways of thinking about it. One is from the quantum side, that I will speak at the end. And the other one is, well, by considering some interaction between dark matter and dark energy. And the second day, we have the nice talk by Nelson on three forms. And three forms, they have, and this is just one example that we'll show here, they intrinsically can have a solution that corresponds to a little signal of the Big Bang. So I will not show an example for dark energy, dark matter that's induced different singularities, but just one, and I will stick to it. So on Nelson's talk, so essentially explain to us what is the dynamic of three forms. So depending on the shape of the potential, which can be of this kind of this one, so the three form at the end you will have, from a background point of view, you have just one bigger freedom. So in this case, essentially you will have at the end kind of a theta, okay? And on the other one, what you have is at some point here is the signal. So what happened is, you can write the equation of motion of a three form like the one corresponding to a scalar field, but with an effective potential. And that effective potential, so you will have that the three form will fall into that the minimum of the potential, or there is another fixed point. Okay? And that other fixed point is the one corresponding to the little signal of the degree, if you have this kind of potential. Okay? So essentially, the three form will enter this regime between minus chi c and chi c, okay, which you can essentially be the gravitational constant. And once it enters this regime, at some point it will turn around and it will hit on the future the little signal of B. So this was just a toy model, and well, a toy model, no. It was a model that we considered, and afterwards this doesn't behave like a scalar field. Okay? And once it hit the, when in the future it would hit a little signal of the Big Bang. So what we did was essentially what happened if there is an interaction between dark matter and dark energy. The dark energy is described by 3. Okay. So we considered, before moving down, let me just show the shape of the dynamical system in absence of interaction. Okay. So in absence of interaction, there are 2 points that are important. One in the past, which is the blue one here, or the blue one here, which corresponds to dark matter. Okay? That point was really hidden because it fixed point at infinity. Okay? So it was not pointed out before in the literature. And then there is the reddish one, which corresponds to the little field. So essentially what happened is essentially this starts at some point in the past at this point, and then it will head here. So the question was, if we switch on the interaction, what will happen? And what happened is that, at least for this phenomenological interaction, okay, so Roy stands for the energy density of dark matter, imply for the energy density of the free field, is that essentially there will be a splitting of the fixed points. Okay? That avoid the little signal of the Big Bang if and only if the interaction terms does not contain rho n. So if the interaction involves rho n, then the little signal is not avoided. If it does not contain it, then the little signal is avoided. Why? Essentially because in that case, energy is being pumped into from the 3 form to the dark matter by the right amount. Okay? So in summary, so for this kind of interaction, phenomenological interaction, the little signal of the Big Bang can be avoided. So through dark matter, dark energy interaction. We also looked at the behavior of this kind of model by using a cosmographic approach. We heard about the cosmographic parameter back on Tuesday, so essentially it's a way of expanding the scale factor. Okay? Instead of exactly the cosmographic parameter, we use the size finder, which are cosmographic parameter, rescaled in such a way that they give 1 at the present for all the redshift for the lambda CD. It's simply a rescaling of the cosmographic parameter. And this is what is shown here. So essentially, the index here is 3, 4, 3, 5. It essentially corresponds to the third derivative of the scale factor, the jerk, if we are dealing with cosmographic parameter 4. So it's the fourth derivative, the fifth derivative. Now, the point 1, 1 corresponds to the Landesidian, okay, and 2. And we consider two kinds of interaction, one which is linear on Brocaille, and the other one which is quadratic. The quadratic one deviates less from the Landesidian, okay? And these points over here, so essentially it's stated one would be which point corresponds at present for the model. So this one over here would be no interaction, linear interaction, and the quadratic interaction. The other thing we did was to look to parameter epsilon, which is essentially the ratio between the logarithmic derivative of the density contrast between this model and Landesidian. So whenever we have 1, so we are essentially at the Landesidian. When there is a deviation, so we are deviating from that. And what happened is that essentially for the linear interaction we deviate more, while for the quadratic interaction we deviate less. In any case, we compared with 3 points from the latest data from SDSS, and what happened is that we are within the error bars. Okay, I should have plotted the error bars, but it's my approach. And the previous result I showed was taking into account all the perturbation. Here we neglect the perturbation of the 3 points. We are currently redoing the calculation starting from an action. So essentially here we start from a phenomenological approach, so to do the perturbation it was not at all easy. And well, on the last 5 minutes, I will describe how can we essentially avoid this kind of singularities in quantum cosmology. Okay? So unfortunately we don't have really a theory of quantum cosmology, but we have several approaches. And here I will essentially speak about one of the approaches which is based on the Wheeler-DeWitt equation. So the Wheeler-DeWitt equation is essentially the Schrödinger equivalent when we are describing the universe as a whole. Okay? For the GR case, it has been, from a background point of view, it has been already worked out from the big rip till the little signal of the big rip. So let me just show you briefly how this is done. So essentially, we need 2 degrees of freedom, one corresponding to matter, so it can be a scalar field, and one corresponding to the geometry. So if we are dealing with the case of the little signal of the big rip, so the scalar field will have this potential, and because it's phantom, it will go up. Okay, instead of going down. And this would be the classical trajectory, but when we are on the quantum regime, these trajectories are longer, so anything is possible. And, well, what we have to do in that case is essentially to look at the Wheeler-DeWitt equation. Okay, we have 2 degrees of freedom. Alpha is the log of the scale factor, so essentially it's codifying the geometry, and phi is described the matter quantity. After some approximation, this case we use a Born-Oppenheimer approximation. As I said, I will try to avoid math as much as possible. One can show that there are solutions in which the wave function vanishes when it approaches this little signal of the big rip. Which means, essentially, that somehow one can express this as the probability of the universe to reach this event is 0, and therefore they are up. Okay, this is essentially known as the wave quantity. We did also the same analysis for some modified theory of gravity. So, how much time do you have? 2. Ooh, yeah, we have 2. Okay, so briefly, so we have several ways of modifying gravity. Okay? So essentially, we can use a Pallavicini approach. So essentially, we have the metric and the connection are somehow, the connection does not correspond to the critical symbol of the metric, okay? And we can also play around with torsion and other ways. So here I will show essentially an example which is inspired on an anything more infinite type of model. So it's described by the action shown here, okay? So at low curvature, we recover essentially GR. While at high curvature, we have deviation. And we have Pallavicini theory, so gamma the connection, and G the metric. Okay? Now, a few years ago, this kind of model was shown that we avoid the Big Bang. So we asked the question, can we avoid also this kind of singularities? And the answer was essentially negative. So the Big Bang cannot be avoided. Okay. So essentially, what happens is that effectively what we will have is a Friedman equation, which is similar to the GR equation. There will be just some modification, but the linear term are still there, so the big cannot be avoided. So therefore, what we tried was to quantize this theory using again an approach similar to the Wheeler-DeWitt equation. So we needed to obtain the Lagrangian. Once we have the Lagrangian, you have the Hamiltonian. Once you have the Hamiltonian, you have the Wheeler-DeWitt equation. But when this is a Palatini type of theory, and most importantly, we have a square root. And instead of inside of the square root, we will have a second derivative of the scale factor compatible with the connection. Okay, and that's not at all easy to from there to get the Hamiltonian. So what we did was essentially to pick up an alternative, a Lagrangian for an action that gives the same equation of motion from a classical point of view, and to quantize that one. And that's what we did. And that was an action proposed by Lasset and Steinhoff back 4 or 5 years ago. Okay? And, well, with this one it was easier. So essentially we have a connection and we have a metric. So we have physical metric with which we measure the distances and the connection with which essentially we describe the geodesy. That connection is compatible with the metric that we use here for the quantization. So after a few calculations, a lot of calculation and going back and forth, we arrived to a Lagrangian. That Lagrangian will give us a Hamiltonian, and that Hamiltonian, over here, is the one that we use to quantize, to get the Wheeler-DeWitt equation. Okay? So summarizing, after some work, we arrived to this Wheeler-DeWitt equation, where we have two, A is the scale factor, and X is essentially the log of the scale factor compatible with the connection. One thing important here is that A, the metric does not enter, is not a dynamical gradient. So the dynamic is essentially connected with the connection, also with the metric compatible with the connection. And what happened again is that we can show that there are solutions in which Wheeler-DeWitt, wave function that's a solution to this Wheeler-DeWitt, Wheeler-DeWitt equation that vanish when A go to infinity, and therefore when we approach the bigger. So in this sense, again, we have the DeWitt criterion is fulfilled, and in that sense, there is now the probability of approaching this event is. Okay, so I tried to give essentially a summary of or review on dark energy singularities, what happened from the perturbative point of view, how could they be avoided by considering dark matter, dark energy interaction. There are many things that I did not mention, but I think I already saw. So whenever you have singularities, we think what's happened on the quantum side. We don't have a theory of quantum theory for gravity or cosmology, so but we can still do something. So using the Wheeler-DeWitt equation, other people use loop quantum cosmology and so forth. And then finally, when I typed my abstract, I didn't know how much time I had, so I also mentioned torsion. So torsion can also be used, or it can play a role in avoiding this kind of singularity. So for some model, what we have seen is that once torsion is switched on, so this what would happen in GR does not happen. So essentially, the energy momentum tensor is modified in such a way that it can bring a kind of interaction between dark matter and dark energy. So thanks for your attention, and I wanted also to thank my collaborator and the student with me.
So we have time for a few questions.
When you drill a simplification, you said that when the scale factor is going to be vanishing, that means you don't take normalization wave function as when you take the wave function in training equation.
What I said is that the Wheeler-DeWitt equation is equivalent to the standard Schrodinger equation when the quantum world is say applied to the universe as a whole. That's what we said.
Yeah, but when we actually when you deal with the wave function training equation, we usually for one particle you take the normalization
Yes, you're right. So yeah, we have here, I didn't define a Hilbert space. So the Hilbert space for the function, for the matter degrees of freedom, they can be defined. Okay, for the geometry is an open problem. Okay, and that's one of the problems with the Wheeler field. So what I mean is essentially, so in this case I was assuming essentially just geometry because it's a perfect fluid. But here, okay. So here you can define, once you have your Oppenheimer approximation with the couple and your regime that is valid, you can have a Hilbert space for the matter side. It's from the geometrical side that you would have a problem. Yes. But for the matter side, there is not.
Why don't you put some matter in, something just in particular, then you have resolved the time problem, and then the Wheeler-DeWitt equation has an evolution, time evolution, like the Schrodinger equation. So you have a time-dependent and a time-independent function.
And what's played a lot of time here after doing the WKB approximation is alpha. So the time is the scale factor essentially.
I'm not sure if I missed something, but you're looking at the interaction between dark matter and dark energy, right?
Well, I essentially first, I went quickly through a review of dark energy singularities, then I said, how can we avoid this? Yeah. From a classical point of view, there are many ways. One of them is interaction between dark matter and matter.
Okay, and did you assume a barotropic equation of state for them? Or
yes.
Yes, with a constant omega over W.
No, only one of, no, in this case for three form, W is not constant. The equation of state is not constant.
Okay.
It reaches constant values in total.
Is there any indication that somehow for any theory for which you achieve cosmic acceleration, you also have necessarily some kind of singularity and finite time and so on? Or it really depends on the model? So you have any general criteria that tells you, okay, this theory has got this particular feature, maybe in the minimum of whatever other thing, or torsion, or it's a Palatini, then you will have some sort of singularity in logical.
You need to look at for the different theories, you need to look at the energy condition. So whenever the null energy condition is violated, then the chance of having some singularity or abrupt events increase. This doesn't mean that all the model that's violate the null energy condition, they will have singularity.
So it's necessary, not sufficient.
Yeah, and one of the reasons I stick to this three model is because they happen if and only if the null energy condition is not fulfilled. The other, you can have them, okay, in the past or even in the future, without, fulfilling it.
So in principle, you can't say even whatever model X this will have or will not have.
Well, if the null energy condition is not fulfilled.
Well, maybe, but not.
Yes, yeah. But most likely in that case.
Okay, so let's thank Mariam again.